In the previous examples of reactions that we've looked at, so we looked at precipitation reactions. Those are when we have a solid that forms as a product. We looked at acid-base reactions. That's where we take something that starts with hydrogen and has hydroxide in it, and that forms water. And we've looked at gas-evolving reactions where we have a gas as a product. All of those different reactions involve exchanging the ions. So taking the cation of one, putting it with the anion of the other to make the products. There are other kinds of reactions also. And one example of those is where instead of just exchanging ions, we actually exchange electrons from one atom to another. And these reactions are called oxidation reduction reactions. And because that's such a long name, we often shorten it to redox reactions. And they frequently, the reason that they got the name oxidation reduction reactions is because they frequently involve oxygen. So that's where the oxidation part comes from. If you look at our chemical reaction here, we're starting with iron as an element and oxygen as an element, and we're forming charged species. So we're getting iron 3 and oxide as our products. So we've exchanged electrons in the process. So frequently these include free elements that turn into ions. And in order for that to happen, we have to either gain or lose electrons. We cannot have an element gain electrons without another element losing them. And so that's why we always have oxidation with reduction. They both have to happen at the same time. So reactions where they're transferred, that's why we call these redox reactions. If our atoms lose electrons, we say that they are being oxidized. If they gain electrons, we say that they are being reduced. And there's some helpful mnemonic devices to help you remember this. So the one that I typically use is oil rig. And oil rig is oxidation is loss, reduction is gain. So oxidation is loss of electrons, and we're always talking about electrons. Reduction is gain of electrons. There's another one that says, Leo the lion says grr. So Leo is loss of electrons is oxidation, and gain of electrons is reduction. So whichever one you prefer, you're welcome to use those, but they just help you remember which one is oxidation and which one is reduction. So let's look at an example. So we're going to take sodium metal reacted with chlorine gas. Both of those are, so sodium metal will ignite in the presence of water and start on fire. Chlorine gas is toxic, but if we combine those, we make sodium chloride, which is table salt. But notice, our sodium is going from no charge to becoming a positive charge, right? So it has lost an electron. Loss of electrons are oxidation. It's giving up its electron. Our chlorine gas is going from no charge to negatively charged, which is the gain of electron is reduction. And so this would be an example of an oxidation reduction reaction. In some chemical reactions, it's pretty easy to determine the flow of electrons, such as if we have a metal or a nonmetal, we can look at the charges to see where those electrons are transferred. Some reactions are not that straightforward, And so we've come up with a way to keep track of the electron flow using something called oxidation state. Many times the oxidation state is going to be equal to the charge of the element. However, sometimes we're going to use it in places where we have covalent bonds. And so they are not charges, even though they look like them. They are imaginary way of keeping track of where the electrons are going. So ion charges are real. We can measure those. Oxidation states are not real. So when we look at assigning oxidation states, many of the times, again, it's going to follow just like the charges. So if we have free elements all by themselves, their oxidation state is going to be 0. So because there is no charge written, that means that our oxidation state is 0. If we have monoatomic ions, okay, the oxidation state is just equal to the charge that those ions would have. And when, just like with charges, if we add up the oxidation states, it has to be a total of 0. So just like for sodium chloride where the charges have to equal 0, our oxidation states also have to have, when added up, be a total of 0. If we have an ion, the oxidation states need to add up to the charge on that ion. So whatever the polyatomic ion is, all of the oxidation states added together are going to equal the charge of the ion. If we have group 1 metals, our oxidation state is equal to the charge. So all group 1 first column metals are going to have an oxidation state of +1. All group 2 row or column 2 metals are going to have an oxidation state of +2, just like their charges would be. When we get to the nonmetals, it gets a little more complicated. For nonmetals, there is an order of priority. So the higher on the list, the more priority that element has. Everything else below it comes after it and takes whatever oxidation states are left. So if we have fluoride, fluoride is going to be a -1. Hydrogen is going to be a +1. And if those two are not present, if we have oxygen, it is usually a -2. Okay. Now, these are guidelines for the nonmetals. So fluorine, hydrogen, oxygen, those are pretty typical, but anything that falls lower than that gets whatever is left. So let's look at an example. So we're going to look at the propanoate anion. And so to assign our oxidation state to these different elements, we know that there are 3 of the carbon, 5 of the hydrogen, and 2 of the oxygen. I'm going to write OX so it doesn't look like 20. If we add all of our oxidation states, it has to be equal to the charge of the anion, which is a -1. Because these are nonmetals, our hydrogen and oxygen are going to take a higher priority, and so we are going to assign those oxidation states first. So hydrogen is a +1. We also have oxygen, which is a -2. So we're going to rearrange this so that we can get our carbon all by itself. So 5 from the hydrogen and a -4 from our oxygen. So if we add those together, we get 3C plus 1 equals minus 1. We're going to move the 1 over to the other side to get our carbons by itself. So 3C equals negative 2. There's 3 of them. So each carbon has a negative 2/3 oxidation state. And so this is why they are not charges, because there's no way we can have 2/3 of an electron to form a charge, but for our oxidation states we can. Here's a practice for you. Assign the oxidation states for each of the following elements. If we look at Br2, Br2 is a free element. It's just bromine by itself, so its oxidation state is 0. Potassium is in the first column of the periodic table, so the charge of potassium is equal to its oxidation state. Now we have a compound, so the total in our compound has to be equal to 0. Lithium is in the first column, so it's plus 1. Fluorine is a minus 1. So you'll notice that these are pretty similar to charges. When we get into the covalent compounds, then it gets a little bit different. So our carbon dioxide, we're going to assign our oxygen first. So it's a minus 2. There are 2 of them. So 2 times minus 2, we have a negative 4 for the oxygen. The whole thing has to equal 0, and so our carbon has to be a plus 4. So 2 times negative 2 gives us a negative 4. Carbon plus a negative 4 equals 0. If we move that to the other side, carbon equals a positive 4. If we look at our sulfate, we're going to assign the oxygen first because it is higher in priority. So for our sulfate, or for the sulfur, 4. We have 4 oxygen. Each oxygen is a minus 2. The whole thing has to equal a negative 2 charge. So our sulfur, if we move that negative 8 over to the other side, the sulfur has to equal a positive 6. Now the next one's a little tricky. Because the sodium is higher priority, we're going to assign the sodium as a plus 1 because there's 2 of them. The cation portion is a plus 2. That means that the O2 needs to be a minus 2 because there's 2 of them. Each oxygen is a minus 1. So this isn't very common, but this is a case where, because the sodium's higher priority, the oxygen gets what's left.